A very warm welcome to this video. We are diving into integration by substitution for classic radical integrals. I will walk you through a trickier example where it's not so clear right away how to choose the substitution function. And we demonstrate this by the following example here. We want to solve the integral of the square root of x squared minus a squared dx. And this a here is a parameter which is larger than 0. Yeah, at the first glance this looks easier as it is, because you might think you can use substitution here for this inner function. However, the derivative of this function is 2x, and there is no 2x outside, so this substitution is not possible and not successful. So we need another trick, and I will tell you the trick. The trick is you make it first more complicated. So you introduce x as a times the hyperbolic cosine of u. You will see later on why this is successful, so just believe me for a moment. So the derivative of dx according to du is a times sine hyperbolic u, and we also change the integration variable dx to a times sine hyperbolic du. So this is slightly different, as I already mentioned, because we make it now more complicated. So x is squared, a squared hyperbolic cosine squared of u. So you see now this new variable is inside. In the previous video we always said u is equal something. Also this is changed because in the previous standard substitution you wrote du dx. So you derive the u according to x. Now we derive the x according to u. It's slightly different. So minus the a squared and this dx part. Okay, so what do you see here? Inside, if you pull out the a squared, what does it mean? It is actually a squared. Let's recall the hyperbolic rules first. So I write here on the right side. If you look up the formula sheet, hyperbolic cosine squared of u minus hyperbolic sine squared of u is equal 1. Similar to trigonometric identities, but here is a minus in between. So what does it mean? We have here inside the cosines, the hyperbolic cosine squared. And if you subtract the one from the right side to the left side, and the sine hyperbolic you write on the right side here. So you can use this here. So it's a squared times cosine squared minus 1, hyperbolic cosine minus 1 is sine hyperbolic squared u. So, and now you see why we have used this kind of substitution, because you can simply take the square root now of that. So the square root of a squared is a, I write in front of the integral. The square root of hyperbolic sine squared is the hyperbolic sine. And the rest we just copy. So now this is the explanation why we first make the integral more complicated, because then the expression inside the root is simplified without here the minus, directly as this function from which we can take the square root simply. Okay, so the problem is if you want to integrate the next one, it is still not so easy. Yeah, the HK you can pull to the right to the front, but you have here hyperbolic sine squared inside, and you cannot use substitution again. Yeah, you cannot now substitute the sine hyperbolic again, because then the inner derivative, you know the story, it's not outside and so on. So we need another trick similar to trigonometric functions. We continue here on the right side. First, remember, what is the hyperbolic cosine of 2u? Recall this from the first semester. So this is hyperbolic cosine squared u plus hyperbolic sine squared u. So if you don't know this, you can look it up again. Then what is this hyperbolic cosine squared? Here, from the first identity, it is just 1 plus hyperbolic sine squared. So what does it mean? What is now my hyperbolic sine, hyperbolic cosine of 2u? It is 1 plus 2 times this. So 2 times this sine, the hyperbolic sine squared. And now we are able to express the hyperbolic sine squared in terms of the hyperbolic cosine without any square functions. So the hyperbolic sine squared of u is then what? It is, I forgot something. Sorry, I forgot something. It's here 2 times. I highlighted it, but it should be 2 times, sorry. So we have here hyperbolic cosine of 2u minus the 1. We shift it to the left side, and then we divide by the 2. But you need here, don't forget the brackets. Great. So substitute this trigonometric hyperbolic identity. You also don't need to derive it. You can directly also look it up on a formulary sheet. So what do we have here? A squared, but 1/2 from this substitution. Probably I don't write it outside. I write it inside, that it you believe it. So 1/2. So this is directly integrable. So what is the integral? So the 2 I wrote into the front, and now the hyperbolic cosine integrated is simply the hyperbolic sine. But what do you need here? Don't forget this 2 here in the linear part inside. You need to divide by the inner derivative. So you have another 1/2 here when integrating this. And the one function integrated is just the u plus constant c. Fine. This is an indefinite integral, and we want the result in x. So what can you do, or what do you have to do actually? You must express from this substitution here the u. So what is the u now? You divide by a and use the inverse of the hyperbolic cosine. So this means the u is the area cosine, hyperbolic cosine of x divided by a. And if you would plug this u function in here, at least you have the result. But it doesn't look so nice, so we do a little more manipulations. At least for this u directly, I would use it, right? But I need another step for this hyperbolic sine of 2u. And we continue here on the right side. What is the hyperbolic sine of 2u? You can look up this identity in the formulary sheet or in the script from the last semester. So it's 2 times hyperbolic sine times hyperbolic cosine. And this we can now use here. Okay. So I think I rewrite the whole line here. It is a squared over 2 over 2, and then here hyperbolic sine, this 1/2 here cancels out with the 2 from the identity, so we just have hyperbolic sine of u times hyperbolic cosine of u minus u plus c. So what do I substitute now? First of all, for this u, I use this function here. So area cos hyperbolic x divided by a. Then for the next one, for this cosine hyperbolic, I can simply use, also if you look here to the substitution we started, it's just x divided by a, right? X divided by a. Get it from here. And for the first part, for the sine hyperbolic, we have to think a little more. Because the sine hyperbolic is equal the square root of the cosine hyperbolic squared, u minus 1. So where does this come from? You directly see it from this formula I've highlighted. No, not from here, sorry. Where is it? From the first line. From the second line, it's visible more clearly. Yeah, hyperbolic sine is square root of hyperbolic cosine squared of u minus 1. From the second line. And now, you know what is cosine hyperbolic u? It's x divided by a once again. So this means this expression is square root of x squared divided by a squared minus 1. Whew. But we are at the end with a very good expression. So what do we have? I sum up x divided by a. I use the same colors as above that you can see it more clearly. The root expression. And then minus area hyperbolic cosine. That's it. Plus the integration constant. So, as you can see here, this is quite a complicated substitution, yeah? The key idea was to substitute with the hyperbolic cosine here so that we get an expression like square root of cosine hyperbolic squared minus 1 without the a squared here, which simplifies to the square root of the sine squared, hyperbolic sine squared, and you can take the root. So this allows to eliminate the square root. This was the idea, the crucial point, which is why substitution in this case is rather challenging. And then, using all these formulas and identities for cosine hyperbolic and sine hyperbolic, we arrive at the end at the reasonably manageable antiderivative. What else you could do here is, if you look up books, if you don't like this area cosine hyperbolic, you can use the ln function instead. You just look up the corresponding identity in the booklet, so you could rewrite it as this expression if you don't like the inverse of hyperbolic cosine functions, because this is more commonly used. Before we stop, I want to give you another example, but I will not completely walk through it. So this integral is given. It is very similar to the one on the left side, but the x and the a variables are swapped. So we have a squared minus x squared instead of x squared minus a squared. And here the hyperbolic sine or cosine does not work. Here you need the trigonometric functions, a times sine of u. This would be successful. Or alternatively, you could also use a times cosine u, also would work analogously. Why does it work? Because if you integrate here and you plug in for the x squared, don't forget the square here, so I don't change the integration variable here, but you see here that you can simplify the square root. You pull out the a squared and then you have 1 minus sine squared, which is the cosine squared of u. So this means the square root will vanish with this square here. So you can cancel this. So if you want to see more details, look to the exercises and to the script. Thanks so much for your attention and see you next time.